This is angular momentum stuff. So we have an object that is rotating in some way, and then we have an interaction. So let's talk about a merry-go-round for a moment. And it's rotating, and it has some angular velocity. And then a little kid jumps on it. What does that do? Well, it's a collision. There should be some conservation of linear momentum, but it's also going to affect the rotation, because what happens is you started out with a circular disk rotating. I is 1/2 I omega squared. So I'm writing what I is. I is 1/2 mr squared. And then it goes to a circular disk with someone on it. And that is I is 1/2 mass times the radius squared plus the mass of the person times their radius squared. It changes the moment of inertia. Anytime there's a change in the moment of inertia, there's a change in the momentum. So let me go ahead and define the momentum here. Let's talk about the sun. There's the sun. You should always draw the sun with solar rays coming off of its little triangles and a little smiley face. Here's the Earth. The Earth is going around like this, and we can pretend it's a point particle. So there's a distance r. The Earth has some mass m, and it's moving with some velocity v. The angular momentum is what we're going to call L, is m r cross v. And in general, we'll just simplify that as mvr, because this is almost always going to be at right angles for rotation. So that's well and good, but this is a point particle. All right, this is well, we can change this. This v is r omega times r. And then what we note is that we have the moment of inertia for a point particle in here. All right, we'll cancel that r and put it up here as r squared. And so we'll have I times omega. And so now, if we have a bunch of other things, like here's Mars going around, and here's Venus going around, and we add up all the planets, we could find the angular momentum of the solar system. Or for the merry-go-round, we add up all the different points, add up their moments of inertia, and so the moment of inertia, which is a vector, is going to be our moment of inertia quantity times the angular velocity. This is our angular momentum. Now, this is nice because we can express this stuff in terms of the forces. We can talk about the change in angular momentum. Well, the moment of inertia might change, or the velocity might change, but in general, this is based on some net torque that is acting on the system. This is analogous to the momentum. The change in momentum over time is the net force. The change in angular momentum is based on the net torque. So what does this mean? Well, it means that if we have a collision, all right, that is an interaction, then there's two things in the system that are interacting. What you will end up with is the final angular momentum equals the initial angular momentum. And so that might be I final omega final equals I initial omega initial for one object plus I initial omega initial for a second object. And then this one might be the second object and I final omega final for the first object. So, this is an expression that looks very much like M1 V1 plus M2 V2 is M1 V1 final plus M2 V2 final. And we'll put initials here. All right. It's an expression that looks the same, but now the moments of inertia could change. And we can have examples where, like this person jumping on a merry-go-round, right? Person jumps on. This is an inelastic collision. The person jumps on and sticks onto the thing. And what you have is that before you had some angular momentum, the person's not rotating, the merry-go-round is. And then afterwards you have a different angular momentum. So we'll walk through how to solve a problem like that. Let's do a merry-go-round. So get us a circular doohickey. There's our circle, and we're going to have a person who is 50 kilograms. And they're going to jump on, and they're going to jump to a point that is 1 meter away. And we're going to simplify this. We're going to say this thing has a radius 1.5 meters and a mass of 100 kilograms. Right? And so we're going to calculate the moment of inertia for the merry-go-round is 1/2 times 100 kilograms times 1.5 meters squared. And so we'll have 1.5 squared times 100 divided by 2 is 112.5. Units for moment of inertia is kilogram meter squared. So when the person jumps on, when they jump on, their moment of inertia is going to be 50 kilograms because they're a point mass jumping on. It's just going to be mr squared times 1 meter squared is 50 kilogram meter squared. So we want to figure out if this thing is rotating, and let's give it a rotation. Omega is 15 radians per second. And if you calculate that out, that is 2 rotations a second. So it's fairly fast. Someone has spun this thing up. It's like 2.4 rotations per second. So they've spun it up. Then they're going to jump on. It's going to slow down. That's what we expect. So what we can look at is the initial angular momentum is going to be L for the merry-go-round plus L for the person, which is I omega plus I omega for the person. And so this is 112.5 kilogram meter squared times 15 radians per second plus, well, the person isn't moving, no angular velocity, so that term is going to be 0. And so we'll have 112.5 times 15 is 1,690. And our units here, the radians are going to go away, and we're going to have kilogram meter squared per second. That is angular momentum. You can massage this into different forms, but there's got to be a mass, a distance, and a velocity in here, and that's what there is. So our final angular velocity has to be this number. And what we have is that it's going to be the total angular momentum. So the total moment of inertia, times the final angular velocity. Well, this total is this number plus this number, which is 162.5 kilogram meter squared times omega final, and that has to equal this 1690. So we'll take this, we'll divide by 162.5, and we'll get that this thing slows down. Omega final is 10.38 radians per second. When we divide this out, all right, we had a radian here we canceled. We were going to cancel a bunch of stuff, and we'll end up with per second, and then we put the radian back in. And so it works. We get something. And this is what we expect. We expect it to slow down. Okay. So this is how collisions work. In general, they're not actual bouncing collisions. We used to have a lab where we could make two disks collide, and in general, they didn't bounce. For angular momentum, if you have an interaction between two objects and you have them actually physically touching, they're probably going to stick together. And so you're going to do something like this. But you might not have, like, we're expanding our definition of collision here. It is an interaction between two chunks of stuff, two things as part of, it's an interaction between the things in the system. So you could have this person jump off the merry-go-round or just walk along the merry-go-round. That's a problem we could have, is what if they were at the center? Then they don't contribute to the moment of inertia until they walk away from the center. And so if you have access to this, try it. Stand at the center of a merry-go-round, have someone spin it up, and then walk towards the edge carefully so you don't, crack your head open. And as you do that, you should possibly notice that it slows down if you stood right at the center. I mean, right on the axis. All right. So it's 12 minutes in. I want to do a problem that doesn't look like a collision. It looks like something else. And this is a trick that people use in satellites. So if you're in astronomy, this is interesting. Have a satellite. Satellites are usually given angular velocity because they're trying to get into space. You put them on a rocket, the rocket spins. So you have to slow that angular velocity down or it can't point at stuff. And so an idea to slow it down, let's say that this satellite is spinning 1 revolution per second. 1 revolution is 2 pi radians, so our angular velocity is 2 pi radians per second. And you can calculate that out, that's 6.28. So the trick to slow it down is to put some of the mass further away. Right? If we spread the mass out, this is what's called the yo-yo trick. We push mass away, and as we push it away, we make the mass contribute a larger moment of inertia. So here, let's calculate what the angular momentum is here. Let's calculate the moment of inertia. Is 1/2 mr squared for basically a spinning cylinder. And then we have a 1 meter radius and a mass of 400 kilograms. So this is 1/2 times 400 kilograms times 1 meter squared is 200 kilogram meter squared. So our angular momentum initially is going to be I omega, and I here is 200 kilogram meter squared times 2 pi radians per second squared. We're going to get rid of the radians, and we'll have 400 pi kilogram meter squared per second. And then you can take that pi and multiply it out. So 400 times pi is about 1260 kilogram meter squared per second. So that is the 1 revolution per second. And we're going to slow it down. There's a typo here. Let's make it 1 revolution per minute. So we want to slow it by a factor of 60. So over here, our final velocity is going to be 1 rev per minute. And that's going to be 2 pi over 60 radians per second. And that's going to be 2 times pi divided by 60 is 0.105 radians per second. So we want to slow it down by a factor of 60 effectively. And the way we're going to do that is put some mass very far away. So the moment of inertia here is I of part A plus the mass that we extend out times its radius squared. So we're going to try to find an expression for that. That's not too bad. This is 1/2. The mass that we left here, what we're going to do is put a kilogram mass. We're going to use 2 of them. So this is 398 kilograms. This is 1 kilogram. This is 1 kilogram. So we'll have 1/2 398 kilograms times its radius is just 1 meter squared plus mass that we put out. We're going to have 2 of these. So we'll have 2 kilograms times r squared. This thing here, I'm running out of room here, but I is going to be, this thing is 199 kilogram meter squared plus 2 kilograms times r squared. So we're going to solve for r, and we have I and omega. So what we have here is L final has to be I final, omega final. We have what I final is now. We've changed the shape of this thing. So we have an expression like this, and we have omega final. And we have what I initial was here. This is 1260 kilogram meter squared per second equals 199 kilogram meter squared plus 2 r squared times 0.105 radians per second. And so the kilograms are all going to cancel out. The meters squared are all going to cancel out. Except here, r squared will have meters in it. The seconds will cancel. The radians go away. And this is just going to be a bunch of math. So I want to divide this over. Let me get another color here. I want to divide. So 1260 divided by 0.105 is 12,000 equals 199 plus 2 times r squared. So we'll subtract over minus 199 and then divide by 2. And so we have an expression for r squared. We take the square root, and r here is 76.8 meters. So this is not too bad. What we do is we build a satellite, if we want to slow it down like this, and we put the extra masses that we don't care about in the satellite. on big cables that are about 150 meters total, 75 on each side roughly. And then when we want to slow it down, we let these masses go, we release the cable, they spin out, they slow everything down, and then we just cut the cables and those masses go away. We don't care about them. And now we're spinning at a reasonable rate. And so this is the thing. There's nowhere in here where there was a collision. This is an object, and the object changed shape. But anytime you have something like that, imagine a figure skater. That's the canonical example, is a figure skater changing the shape of their body. Or if you've seen the lab video, which I know at least half of you have, because I can look at the statistics. I don't know why you've seen it before this week. But you can see I have these weights held out. Then I change the shape of my body. That's not a collision. That's just I change my moment of inertia, and it changes my angular velocity. And this is, if you work this backwards, you can solve that problem. You go from, this is me spinning slowly, this is me spinning fast. And I kind of nicely divided this up like that, so that there's an initial side and a final side. So that's going to conclude the video because that's about 20 minutes. If y'all have any questions on energy or momentum, please email me. I cannot possibly do every problem that you could expect, but I've done many of them that I've wanted to do. But maybe there's something that you're seeing that I'm not. So please email me. Let me know if you need anything.